Alright, so there's been a lot of confusion about these terracotta pot, Tealight, room heating systems. What I'm going to do is go over the physics behind how these things work, explain the general idea for all of you that haven't heard of it before, which you probably have, otherwise you wouldn't be watching this video. And then I'll go over how practical it is in the home and all that kind of stuff. So step one, we need to look at the system itself and how it works. The idea here is we have a candle, and usually a candle just releases a pillar of hot air that goes straight up towards the ceiling and isn't very useful to the occupants because most occupants do not live on their ceilings. However, with the terracotta pot system, we are able to absorb the heat that the candle produces and then redistribute it outward this way, and still this way, so that not all of the heat ends up in this useless pillar that goes up to the sky and does nothing. So, what's important to remember here is if this thing is producing, what was it? My calculations show that it produces approximately 34 watts. If it's producing 34 watts, then no terracotta pots or any amount of magic is going to make that 34 watts bigger than it already is. If this is 34 watts here being produced and going into the pot, then you're going to have 34 watts coming out of your pot. If you find that your terracotta pot is releasing more than 34 watts, if your candle is producing only 34 watts, then please contact a physicist so that he can capture and study your pot because you have successfully broken the universe. So, the concept. If your candle produces 34 watts, the pot emits and radiates the 34 watts. The advantage of the terracotta pot system is that instead of getting a useless pillar of heat that goes towards the ceiling, you are spreading it out and turning it into usable heat that's going to warm up your room much more evenly. Okay, now let's go over some very basic concepts in thermodynamics, or rather heat transfer, and show how this is going to affect your house with science. Now, we have a wall. This wall can be used to simulate the wall of the terracotta pot or of the house or of anything in heat transfer. We're just looking at the very basic concepts. This is a wall. Now, if you have a hot side and a cold side, you're going to get heat transfer happening through your wall. And that heat transfer going this way means that you're going from the hot side to the cold side. That's always going to be the way it works. You can't go from the cold side to the hot side unless you have a heat pump or something magical like that. The mechanic for how this works, the equation for how this works, and this is a simplified equation, that's a little bit of an approximation, is Q dot equals K delta T. Now what this means is our Q dot is our arrow, and that means how much energy is going through the wall in the form of heat. Our K has to do with our wall's thickness and surface area and all that jazz, and it just has to do with how much our wall is going to resist the transfer of heat. This delta T over here is just fancy notation for hot minus cold. So our only real variables that we're going to be working with are our arrow, our hot side, our cold side, and how much does our wall resist it. Now, that's one way of looking at it. The other way of looking at it is we can push heat through our wall, and that's kind of what's happening here. If we have a candle, this is a candle, and the only way for the heat of that candle to escape is to go through this wall, then you are pushing heat through the wall, and if you're pushing it through the wall in a certain direction with a certain magnitude, then you're going to end up with a hot side over here, and assuming it's exposed to the air, you'll have a cold side over here for things to cool down. So one way is you can have hot, you can have cold, and then you'll get a resulting arrow that comes from your hot and your cold. Another way is that you can be pushing heat through the wall and you get a resultant hot and cold side. Both of those situations you can use this equation, and we're going to take advantage of this relationship to solve our problem. Step one, we need to prove that we have 34 watts and not some other magical number. Once we have proven that we have 34 watts, we can look at how much energy we lose in our house due to heat and then we can start looking at the practicality of this situation. So, how do we prove that we have 34 watts coming out of our candle? This is where I get to do a little bit of physics. If you don't really care how I prove it's 34 watts, then you can jump ahead to a later part in the video. If you do want to see it, then you're going to have to bear with me, because now I'm going to be looking at my little piece of paper that I already did all the math on. So I went to the IKEA website and I found these little tea candle lighting thingies, and they were $4 for 100 candles. So that is 4 cents per candle. All I'm trying to do here is get the numbers straight so that I can do my math with my numbers and I don't have to be jumping back and forth between math and finding numbers. So that's number one that I need, is how expensive is a candle. The next thing is, how long does the candle burn for? These things burn for about 4.5 hours. Next thing is, how much weight do I have in one single candle? I need to know the mass of the paraffin wax. And by knowing the mass of the paraffin wax, I'm going to eventually be able to figure out how hot the thing burns. Well, looking at the website, a pack of 100 of these things weighs 3 pounds. So that works out to 13.6 grams per candle. Now, I think that that mass also contains the weight of the packaging and the metal and all that jazz. So I did a little bit of hunting, and I found this this forum post thingy, and Chris Egerton did a very similar calculation to what I'm doing, where he figured out from his own measurements that it was 13.03 grams of wax in a candle. That's a little bit more conservative, and it should account for the packaging and all that, so I'm going to use his number, 13.03. It's a better number. The next thing that we need to know is the combustion energy density of the paraffin wax in the candle. What this allows us to do is say, for 13 grams of wax, we're going to have X amount of energy. And that amount of energy is 42 kilojoules per, I was going to say kilogram, but it's just grams. Okay, 42 kilojoules per kilograms and 13.03 grams together will give us a number of, let me just write this down in another color, this, and I'll draw my arrows later. 13.03 grams times 42 kilojoules per gram is going to give us 547.26 kilojoules. 547.26 kilojoules. Now what we also need to do is, we have an amount of energy in the entire candle, but in order to get the amount of energy that this thing is going to burn over time, we need to consider our 4.5 hours over here. So what we need to do is first convert our hours into seconds. 4.5 hours times 3,600 seconds in 1 hour is going to be equal to 16,200 seconds. And now if I say 547.26 kilojoules divided by 16,200 seconds, then that's going to work out to an amount of 33.78 watts, or the number that I've been using. I just rounded up and used 34 watts at the beginning. So that's the magic of where this number comes from. And if you end up following what Chris Egerton did down here, he made some slight variations in the way that he did his calculation, and he comes out with 33.8 watts, which is the same as mine, just rounded to 1 decimal place instead of 2. Okay, So now we have confirmed that our candle is in fact producing 34 watts. I'm not crazy. So our next step is to look at the house heating scenario. Okay, we know we are producing 34 watts. This is our heat source. This is our candle. We've got 34 watts right here. Now instead of having a wall, we're going to have a house, which is a little bit more practical. And in our house, we have our heat source. Our heat source is doing 34 watts. That 34 watts is going to come out of the thing and then go out of the house. Alright, we want to do some solving here and figure out, what I'm going to do is figure out how many candles you need in order to keep your house warm. And I'm going to use that to see if we're being practical. So what I actually want to find in this case is how many watts do I need to be producing in this spot here where I wrote 34. I want to find a new number to put in this spot here so that if I have an outside temperature of 5 degrees Celsius, I can have an inside temperature of 22.5 degrees Celsius. And for you poor sad Americans who don't understand Celsius, 22.5 is room temperature and 5 degrees Celsius is a crisp winter morning, depending on the time of winter, probably late January, crisp winter morning. I'm from Vancouver, Canada, so you can consider that however you will. Anyways, how do we solve this? We've got our heat source, we've got our temperature difference, we need to find a K, and then we can find the magnitude of our Q using this wonderful little formula here. So how on earth are we going to find a K for a house? That seems like kind of a difficult thing to calculate. Well, fortunately, people have calculated this before, because if they hadn't, I would have spent hours and hours and hours trying to figure out how to calculate for each of the individual walls with convection, radiation, and conduction, and then linearizing it into one variable K, which would have been this awful hell. Luckily, someone's done this. I'm good to go. So I punch in all of the information for a standard house. In this, I said I'm going to deal with one room, and it's just 20 square feet, and that's the whole house. Just one 20 square foot room. And this is going to be pretty conservative because the bigger your house gets, the better your volume to surface area ratio is going to get, and the better your heat energy conservation per unit volume is going to be, if that makes any sense. It's just better to have a bigger house. So me saying a small house is being conservative. That's all you really need to know. I looked at two scenarios here. I said I want my inside temperature to be 10 degrees Celsius, which is pretty cold, while the outside is 5 degrees Celsius, or I want my inside temperature to be room temperature when the outside is 5 degrees Celsius. Coming down here, the program spat out these numbers for me, changing all these values to be normal house values. Now, using these values, we can do our magic and figure out what our K is going to be, and when we do that, we'll be able to do all of the math very, very easily to figure out everything else. Now, if we want to do the very basic calculation of how many candles do we need in order to heat up our house to 22.5 degrees Celsius, then we can take this straight number actually, and we already figured out it's 34 watts. So if we take this kilowatt hours per year and convert that into watts, which I did on one of these many papers over here. Let's see, what does that work out to? Alright, let me write this down. Doing magical conversion science. This one works out to 255 watts approximately, and this one works out to 883 watts approximately. And I'm getting this from the sticky notes that I made a couple hours ago when I was curiously watching YouTube videos and saying, I wonder. Okay, now, we have our 883 watts that the house is consistently losing throughout the year. We know that our candle produces, our magical candle, not magical, actually, it's just a candle. Our candle produces 34 watts, and our house at 22.5 degrees Celsius is losing 883 watts. So in order for us to make that 883 watts with our candles, which will allow us to keep our 22.5 degrees Celsius comfortable room temperature, we are going to need 883 divided by 34 candles. And this number works out to be 883, where did I put it? It works out to be 26.1 candles. 26.1 candles. Or you can have 27 candles and have it be slightly warmer, or 26 candles and be slightly colder. I think you get the idea. On the other hand, if we do not need a comfortable room temperature and we're okay with our cold 10 degrees Celsius because we have a coat, we just want it to be not 5. Then what we can do is take our 255, divide that by 34, and our number of candles for our uncomfortable room temperature is going to be 7.5. And let me move that so it makes a little bit more sense. Okay. So, in short, what the heck just happened here? We've got our terracotta pot light tea candle thing that's producing energy. We want to see if it's practical for us to heat our house with that energy. So we figure out how many watts we're producing. We look at science. We figure out that if the outside temperature is 5 degrees and the inside temperature is 22.5 degrees, then we are losing 883 watts. So we take that 883 watts and we divide by the watts produced by a single candle so that we can get, I should draw this, if we're losing 883 watts this way, and that's the number that came off of this website down here, this website that I should give credit to, because I personally don't like lawsuits, but I don't think I wrote down the website, so I'm just going to have to put it in the video description. But we have 883 watts going out, so in order to maintain our temperature, we also have to have 883 watts coming in through here, and then we can stay at our comfortable 22.5 degrees Celsius. In order for that to happen, we have to have 26.1 candles going all at the same time consistently throughout the day. So that's your solution. This is for 20 square feet or 20 square meters? I think it was 20 square meters. Yes. For a 20 square meter room, you need 26.1 candles going on a crisp winter morning in order to keep it at a nice room temperature. Now, you can think to yourself, that might be reasonable, that might not be reasonable. I don't know, that's up to you. I don't really think it's reasonable, and here's the reason why I don't think it's entirely reasonable. If you look at the cost of producing this energy, let's actually do that calculation right now. That's on my paper too. The cost of one candle is 4 cents, as we indicated over here, and that's why I wrote it down, so that we could do this calculation. So we have a 4-cent candle. That candle, in its lifetime, is going to produce this many kilojoules in that candle's lifetime. Now we can convert that into kilowatt hours. That many kilojoules, what we have to do is times 1 hour divided by 3,600 seconds, and through magic that turns us into kilowatt hours. That becomes 0.152 kilowatt hours. Now, if we look over here, I went online and I went to my city's website for how much we pay to get our electricity. If I want to get 1 kilowatt hour of electricity, then I am paying 11.2 cents. You can look at the website and see how this works. Basically, if you don't use very much electricity at all, you're paying the wonderful grandma fee, and if you do use electricity like a standard human being, you're in step 2, and you're paying 11.27 cents per kilowatt hour. So we take that number, 11.72 cents per kilowatt hour, and we multiply that by our 0.152 kilowatt hours times 11 point, what was it? I'm going crazy. I can't remember anything. 11 point something cents per kilowatt hour. And the amount of money that we get for the electricity is 1.71 cents. Now what does this mean? This means that we've produced this much energy from the candle at the cost of 4 cents. That's with our candle. But if we were to use an electrical heater instead and produce the same amount of energy, then it only costed us 1.71 cents. So if you really, really want to, you could make yourself a terracotta pot lamp heater thing, but you're going to be spending more than twice as much money for the same heating effect as if you were to use an electrical heater. Let that sink in for a sec. So then what's going to be the point of these terracotta lamp things? Well, the point is they can potentially look pretty. And if you like candlelight and you like reading by candlelight or watching a movie by candlelight, then you can show people your cool heating device thing. Those of you who have ugly heating device things, you might want to rethink that. Or if you're stranded out in the middle of nowhere and you have nothing else to do, but you happen to have terracotta pots and tea candle things, then you can use your terracotta pot tea candle device. Hujimotsu. But in the end, not practical for financial reasons. I might use one like this because I do like candlelight. It's nice, it's pleasant, and it has the potential to look pretty. But in the end, that's the physics. I also made a spreadsheet of all this. I turned it into a spreadsheet so that people who are not physicists can do their own calculations, and I will upload the spreadsheet and you can use it to calculate your own terracotta pot lamp heating need things, and graph them and have a wonderful experience with science. You just put in your numbers here, it gives you your numbers here. What this is able to prove is that each candle is producing 0.67 degrees Celsius, so that makes it very easy for you to calculate how many candles you need to get to your desired temperature. So yeah, that's it. Is it practical? Is it not practical? Do you want one? I don't know. It's up to you. But now you've seen the numbers, you've seen how it works, and that ends my video.